experimental and FEM analysis of orthodontic mini-implant design on primary stability. In this presentation, our goal is to offer you a quick summary of the research and conclusions. Please follow the links to view the research and further details. Thanks to all the authors and publishers for making this research public, thereby advancing science and innovation. Please like, share, and subscribe. The main objective of this research is to establish a connection between orthodontic mini-implant design, pull-out force, and primary stability by comparing two commercial mini-implants or temporary anchorage devices, Thomas pin and perfect anchor. Mini-implant geometric analysis and quantification of bone characteristics are performed, whereupon experimental in vitro pull-out test is conducted. With the use of CAISA, Computer-Aided Three-Dimensional Interactive Application, CAD, Computer-Aided Design, CAM, Computer-Aided Manufacturing, and K, Computer-Aided Engineering System, 3D models of mini-implants and bone segments are created. Afterwards, those same models are imported into Abacus software, where finite element models are generated with a special focus on material properties, boundary conditions, and interactions. FEM, finite element method analysis, is used to stimulate the pull-out test. Then, the results of the structural analysis are compared with the experimental results. The FEM analysis results contain information about maximum stresses on implant bone system caused to the pull-out force. It is determined that the core diameter of a screw thread and conicity are the main factors of the mini-implant design that have a direct impact on primary stability. In summary, stresses generated on the Thomas pin model are lower than stresses on the perfect anchor, even though Thomas pin endures greater pull-out forces. The implant system with implemented Thomas pin still represents a more stressed system due to the uniform distribution of stresses with bigger values.